Formulation of slab waveguide analysis. This is going to be a rather mathematically intense video, and I apologize for that, but it is immensely important. This is going to be a great example of how we can start with a physical problem and go through all of the steps to solve it numerically. And so first we'll step through the formulation. That's where we derive all the equations we'll need, and then we'll discuss the solution of this. So this is a really common theme in computation where we start off with a formulation and we have equations all over the place. But what happens most often in literature and in textbooks is it just stops there and it says, okay, then you know everything. Well, what if we don't? And so what I like to do is discuss formulation, equations flying everywhere. But then after that, we have to discuss the implementation where we pull out the key equations and we list our algorithm that your program does step 1, step 2, step 3 until it analyzes the slab waveguide. In this video, we're focusing almost exclusively on the formulation. We'll discuss a little bit about the solution near the end, but the implementation will follow in another video. So in our case for formulation, we're solving an electromagnetic problem, so we will start off with Maxwell's curl equations. We will do a whole bunch of stuff, and we'll end up with a matrix equation that has the form of an eigenvalue problem. And this is where we'll solve that to calculate the electromagnetic modes of the waveguide. The solution of this will come in a later video. We're just discussing really going from Maxwell's curl equations to that eigenvalue problem. So let's get right into this. Formulation. Well, as we mentioned, this is an electromagnetics problem, and more specifically, an electrodynamics problem with waves. And so we're going to start with Maxwell's curl equations because it's these two things that predict electromagnetic waves. And as promised, I'm not going to delve too much into the electromagnetic theory, just enough to understand how we're formulating. Now, inherent in this equation is this del cross and then some vector quantity. This is called a curl calculation, and it is calculating the tendency of a vector function to circulate about some axis. So if we look at this little animation over here, we can actually see that there's some circulation in the field here. And so what these two curl equations are saying is that if there's any circulation in the electric field, that means there has to be an oscillating magnetic field down the axis of that circulation. And the other curl equation says basically the opposite thing. If there's a circulation in the magnetic field, we will have an oscillating electric field. And one of these equations has a minus, the other doesn't. And in the end, one field oscillates around the other and it goes back and forth, and we get electromagnetic waves. We don't need to know any of that. So in this video, we can kind of just pretend we're mathematicians and we're handed this set of equations and we would like to solve it. But if we expand this curl calculation, this is what that looks like in Cartesian coordinates, and we will use this on the next slide. So we'll take this first equation where the curl of the electric field equals a negative oscillating magnetic field. That is a vector equation, and so we can expand that into its vector components. We'll choose to work in Cartesian coordinates. So on the left, we've expanded that curl operation, and on the right, we've expanded the magnetic field into its x, y, and z components. And then in the very last step, we multiply out the entire right-hand side of the equation. So this minus j omega mu is now multiplying each of those three vector components. So we still have a single vector equation. What we'll do is set the x component on the left equal to the x component on the right. We will set the y component on the left equal to the y component on the right. We will set the z component on the left equal to the z component on the right. And then we go from a single vector equation to three scalar and coupled partial differential equations. So in fact, we did that with the first curl equation. We could easily do that with the second. I will skip the work, But the final answer is that we now have 6 coupled partial differential equations. We just derived that first step, but if we did the exact same thing to our second curl equation, we'd end up with an additional 3 equations. And so we have a set of 6 coupled partial differential equations that we need to work with. Now this is looking complicated, but I promise you at the end we have a very simple solution. One of the reasons things are as complicated as they are is because that's for fully 3-dimensional problems. But it turns out we can reduce ours to just 1 dimension. And what we're showing here is our slab waveguide. So we have some high index regions surrounded by 2 low index regions. And we're drawing a guided mode that's propagating in the z direction. Let's first think about the x direction. Well, in the x direction, material properties are changing. And from previous discussions, we know we have a mode profile that changes in the x direction. So things are changing in the x direction, and we can't do anything with it. So let's go on and look at y. In the y direction, the device is uniform. Our mode is uniform. There's no oscillation or propagation in the y direction. Literally nothing happens in the y direction. Everything stays the same. So that has to mean if we try to take a derivative in the y direction, that will be 0 if nothing is changing in the y direction. So we'll go into Maxwell's equations, and anytime there's a y derivative, we'll set that equal to 0, and that will clearly simplify things. We'll get more into the z direction, but notice the device is uniform in the z direction. That doesn't change. However, the wave does oscillate in the z direction. The wave accumulates phase, and it will turn out that we can replace our z derivatives with minus j beta, where beta is that phase constant describing how much phase or how quickly the modes accumulate the phase. Let's first apply the fact that our y derivative is 0. Nothing is changing in the y derivative. So we look through our 6 coupled partial differential equations and we identify y derivatives. There's one here, there's one here, there's one here, there's one here, and we want to cross them off. That gives us a reduced set of equations. We're missing the y derivative terms. Now, when this happens, something magical has happened to our equations, and we would have to stare at these equations for a while, maybe to figure out exactly what that is. Let's talk about this on the next slide. I have color-coded those same 6 equations from the previous slide. Otherwise, they remain unchanged. And what we'll notice here is that all the equations in blue contain certain set of field terms, contains hx, hz, and ey. None of those terms appear in the red equations. The red equations contain ex, ez, and hy, and none of those appear in blue equations. So in fact, our set of 6 coupled partial differential equations has decoupled into 2 independent sets of 3 equations each. This first one we will call the EY mode. And why are we choosing that? Because there's only one electric field quantity over here, whereas there's 2, and that 2 magnetic fields. So since there's only one electric field quantity and it's EY, it makes sense. Let's call that the EY mode. Likewise, while there's 2 electric fields for the second one, there's only one magnetic field quantity, and that's HY. So let's just call this the HY mode. And these are completely independent sets of equations. So if we wanted to know everything about our waveguide, we would have to solve both of these separately, differently, get different solutions, and understand that both of these could be happening. Now, these sets of equations, they look very similar. So we'll just choose the EY mode and proceed with that in this video. But everything we're going to do to the EY mode, we would simply do to the HY mode, and we would get solutions for that in the end too. What about the Z direction? So we know that the form of our solution has to look like this. So we have an electric field, X, Y, and Z. We live in a 3-dimensional world, has to be in 3 dimensions. This Y direction, nothing changes. So actually, you don't really have to write that here. What's left is the dependence on X and Z. And it turns out we can write our solution in this form, which is very useful. and it's the product of two independent things. The second term is describing the oscillations in the z direction, where this beta is the phase constant, describing how quickly it oscillates or how quickly it accumulates phase in the z direction. Then we have this envelope term that's describing how the amplitude changes as a function of x. And in fact, this does not change. The modes stay looking the same. They just simply accumulate phase as they propagate. Given that, what happens if we try to take a z derivative of the electric field? Well, that means we're taking the z derivative of this envelope terms times e to the minus j beta z. Well, this envelope term is not a function of z. That can come to the outside of a derivative operation, and that's where we are here. Or we can also think of it as a product rule, whereas we have the amplitude term times the derivative of the exponential plus the exponential times the derivative of the amplitude term. But as we mentioned, the amplitude term is not a function of z, so that would reduce to 0, and this term crosses off. So we're here now, and we need to apply our z derivative to e to the minus j beta z. Well, that's easy. The minus j beta comes to the outside, and we just have the e to the minus j beta z again. So we have minus j beta times our envelope function times e to the minus j beta z. Well, this envelope term times e to the minus j beta z, that's the original electric field. So let's write it that way. Minus j beta times the original electric field. So if I now compare what we had first, derivative with respect to z of the electric field is equal to minus j beta times the original electric field, that shows us that any derivative in the z direction is simply minus j beta. And that's because the only thing that is happening in the z direction is our wave is accumulating phase, and it's this phase constant that tells us how quickly that happens. So it makes a bit intuitive sense that this would happen. So here's our set of 3 equations for that EY mode, and I've sort of color-coded, identified our z derivatives. We're simply going to replace those with minus j beta. And when we do that, we end up here. Looking a little bit simpler, and we still have a little bit more work to do, but we're getting there. One last thing has happened. We had partial derivatives up here with respect to x and with respect to z. However, once we've eliminated the partial derivative with respect to z, there's only one independent variable left, and that's x. So we don't need to write a partial derivative. We can write an ordinary derivative because there's only one independent variable left. Now in computation, we always want to normalize things. And the way we're going to normalize our spatial coordinates is to put everything in terms of wavelength. That way our dimensions aren't like, 10.2 times 10 to the minus 6 meters or really ugly numbers like that. We would rather just express our dimensions as this dimension is 3 wavelengths or 5 wavelengths. And there's really no units then. It's just a 5 or a 3. And so we would do that by dividing by wavelength. And so if we divide all distances by wavelength, we've normalized it, and our units of meters or centimeters or micrometers or whatever units we're using has dropped out. Now I've written question marks here because we'll ask ourselves, is this really the best way to do it? Well, in fact, I do think it's the best way, but we're going to do something slightly different. Instead of dividing by wavelength, we are going to multiply by the free space wave number, which is equal to 2 pi divided by wavelength. So we are dividing by wavelength, but we also happen to be multiplying by 2 pi. Now, we don't really want to multiply by 2 pi. That just happens to be there in the free space wave number. But something very convenient happens when we multiply by the free space wave number. So let's go ahead and apply this to our equations and normalize that spatial coordinate x and see what happens. So let's take our first equation, which just has our standard x in it. So we're going to replace x with our normalized x that we're writing with the little squiggly over top and divide it by k naught. Because remember, our normalized coordinate is k naught times x. Therefore, x has to be our normalized x divided by k naught. So we have the normalized x in the denominator, which means we have to multiply by k naught out here. At this point, let's divide the entire equation by k naught. When we do that, well, the k naught disappears here. I end up with this first term being divided by k naught. So I'm going to associate that with the beta divided by k naught. And then over on the right, our j omega epsilon divided by k naught. Well, remember when we were discussing the phase constant? It was k naught times our effective refractive index. So, well, here we have our beta divided by k naught. So in fact, this ratio is just the effective refractive index. No k naught multiplying this term, but we still have this expression here. And we can manipulate this a little bit. So what we're going to do is expand k naught, because that's also equal to omega times the square root of the free space permeability times the free space permittivity. And now we see that the free space permittivity occurs in two places, and we can simplify a little bit, and then we end up with J times the square root times the relative permittivity times the electric field Y. And it actually turns out that this ratio is 1 divided by the free space impedance, and we could replace it, maybe make things look a little bit simpler, but we'll just retain that and not worry too much about it. So it doesn't appear we've simplified this too much, but it'll turn out to get much simpler in the next slide. Okay, so we can apply that same normalization to all three of our equations for the EY mode, and we end up here. So at optical frequencies, our relative permeability is 1. In fact, above a gigahertz, it's very difficult to find materials that have any kind of permeability. If we wanted permeability, we'd have to use something called metamaterials, which is beyond the scope of what we're talking about here, but a fascinating subject. So assuming we're doing an optical analysis, we will just set our relative permeability to 1, and that falls out of our set of 3 equations. Okay. So we have our 3 equations where we've normalized our x coordinate and we've dropped the free space permeability. What we're going to do is take these second and third equations and solve them for the magnetic field. So this second equation we will solve for h sub x, and our third equation we will solve for h sub z, and we get these 2 expressions. So we now have hx and hz both in terms of EY. So what we'll do next is we'll take this expression for hx and plug it in here to replace hx. We'll take our second expression for hz and we'll plug it in here to get rid of hz, and we'll have a single equation just in terms of EY. So here's what happens when we do that. We have our first equation, which was just a copy from up here. We plug in our expression for hx, our expression for hy, and then we turn our simplifying crank, and look at this. Look how easy and simple that is. And it wouldn't have been that easy and simple if we didn't normalize by multiplying by k naught. So I'm just going to write this in a slightly different form. We'll have our second order derivative plus epsilon times E equals effective refractive index squared times the electric field. And there's a purpose that we wrote it this way, and that's what we'll talk about on the next slide. So it turns out the reason we wrote it this way is because that is in the form of what is called an eigenvalue problem. So eigenvalue problems have the form of AX equals lambda X, where A is a square matrix, X is a column vector, this X is the same X, it's a column vector, and lambda is a constant. And analytically, we can write our eigenvalue problem this way. And we can think of an eigenvalue problem like this. Suppose we have a guess as to what the electric field would look like, one of our mode solutions. If we can do all of this math to it and get the original function back just scaled by a constant, that is a valid answer to this. That's a solution to our eigenvalue problem. But because it has to follow these rules, there's only certain discrete answers that we will get. So we have put our original 2 curl equations, we expanded them into 6 coupled partial differential equations, we did a whole bunch of stuff, and then came down to one single equation that's in the form of an eigenvalue problem. We have one last thing to do. We're going to put our differential equation into matrix form, and we'll do this going term by term, and we don't explicitly have to touch finite differences. We have a second order derivative, so we have a second order derivative matrix. We have our refractive index squared doing a point-by-point multiplication onto the electric field. So N becomes a diagonal matrix with the refractive index through the cross-section of the slab running through the diagonal of a matrix. And of course, we're squaring it. Our electric field in the cross-section of the slab waveguide is stored in a column vector. We have our effective refractive index squared. That's just a scalar constant, so we just copy that down here. And our electric field, again, stored in a column vector. Alternatively, just a slight tweak on this, rather than have the effective refractive index squared, we could just simply have the relative permittivity. So if we know the relative permittivity through the cross-section of the slab waveguide, we could just run those values down the diagonal of this matrix. So it's also a diagonal of a matrix. This is a diagonal matrix of refractive index squared, diagonal matrix of relative permittivity, and we're saying the same thing. Optics people like to talk in terms of refractive index, so this might be preferred for an optics person, and maybe the one down here might be preferred for more of a radio frequency or microwave person, but both lead to the same answer. The big square matrix on the left is called the eigenmatrix. And this scalar value here is called the eigenvalue. Let's talk more about the solution, not how to find it, but given that solution, how does it relate to these matrices and what does it look like? So we start with our matrix eigenvalue problem. And in MATLAB, this is very easy. We will simply say A equals D2x plus epsilon. That's one line of code. In a second line of code, we call Eig, and we'll say something like V comma D equals Eig of this A matrix. And out comes two matrices, V, and in MATLAB code, I usually call it D, but more symbolically, we'll call this lambda because this is our eigenvalues, and we've been using lambda for that, not wavelength, just we're running out of letters, I guess. So we solve our eigenvalue problem. We get an eigenvector matrix, and we get a diagonal matrix of the eigenvalues. Let's think about what these look like. So our eigenvector matrix, if we look at the columns, these are the electric fields associated with each of the modes that we're calculating. And if we, in our cross-section of the slab, used m number of points, then we will only be able to calculate m number of modes. Truly, in principle, an eigenvalue problem always has an infinite number of solutions, but because we're resolving this numerically, we can only resolve so many of them. And we'll get as many modes as we have points. Now, they may not all be guided modes, but they will be eigenmodes of that matrix equation. And they're running down the column. So if we grab this and plotted it, we would see pictures of each of these modes. Then our eigenvalue matrix has the eigenvalues associated with them. So these are our effective refractive indices of the modes. Now, the real important thing to realize is that our eigenvectors and eigenvalues come in pairs, and we can't mix these up. So the eigenvector is what the mode looks like. This effective refractive index is describing how fast it propagates or how quickly it accumulates phase. And so this is the effective refractive index of this mode. We don't want to mix these up in any way. So the second eigenvalue goes with the second eigenvector and so on. So we don't want to mix those up. We can look at this more as pictures. As I mentioned, these eigenvectors are pictures of the modes. So rather than just draw it as numbers, we could draw it like this. And if we plotted them, those are literally the pictures that we would see. So the columns of the eigenvector matrix are pictures of the modes. If we wanted to, we could plot those over top of our original slab waveguide. And now they truly do look like guided modes. And the eigenvalues are the square of our effective refractive indices. So in order to get the effective refractive indices, we would simply take the square root of our eigenvalues. From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.